Jonas Montud. This is Guru Data.
And we both today are going to present a short, brief introduction about nanocrystalline diamond biosensing.
Biosensors pertain to sensing or detection of chemical or biological interactions or agents by the transducer method, which does not depend on any special dyes, enzymes, or radio labels. So in order to fabricate or build our biosensor, we need to know why we would even use a particular type of material for the biosensor. One of the materials we could use is nanocrystalline diamonds. And the reason for using the crystalline diamonds would be because, one, they're extremely chemically stable when they're used as electrodes in materials with a wide range of electrochemical potential windows. They normally have low background noise. They generally reduce non-specific protein binding, and they're very dimensionally stable. The reason is because of the small size of nanocrystalline diamonds. They're very good for use in electrodes. Another reason is because of the ultra smooth surface. This morphology allows them to deposit a more uniform and dense and conformal coverage of monolayers on the surface of your device. The next step requires that you deposit a 500 nanometer thick SiO2 layer using plasma-enhanced chemical vapor deposition. After this, an oxide is patterned using a 1.7 micrometer thick positive resist, followed by a wet etching of the oxide layer using a 10:1 ratio of buffer oxide etchant for about 15 minutes. The next step requires that you dry etch the nanocrystalline diamonds with a reactive ion etching of oxygen and silicon hexafluoride gas mixture through the oxide hard mass formed in the previous steps to form MEAs, electrical contact pads, and the electrical lines between them. And in the next sample, I'll show those things. We deposit another 500 nanometer thick of silicon dioxide film by plasma-enhanced chemical vapor deposition, and then you wet etch the SiO2 to open up the NCD microelectrode, which is about 200 micrometers, and then also the contact pads to form MEAs, electrical contact pads, and the electrical lines between them. And in the next sample, I'll show those things. We deposit another 500 nanometer thick of silicon dioxide film by plasma-enhanced chemical vapor deposition, and then you wet etch the SiO2 to open up the NCD microelectrode, which is about 200 micrometers, and then also the contact pad. Step, the silicon dioxide film was grown to 1 micrometer thick, and this was found to be very adequate for passivation, underlying that the nanocrystalline diamond which form the electrolyte. Now if you look at this closer, these are the contact pads towards the edges, and in the center, these are the electrodes. So right here on the computer screen, you could see some SEM images.
Now when we study the electrochemical property of this fabricated patterned nanocrystalline diamond chip, we use electrochemical impedance spectroscopical instrument that's called Autolab potentiostat. This one here is the instrument. It's called Autolab PGstat 302N, and here by 3 electrode setup using a platinum coil as a counter electrode and saturated calomel electrode as a reference electrode, we analyze the electrochemical response of this fabricated NCD diamond chip. Then we place this cell in this Faraday. After loading the cell on the Faraday cage, switch on the cell on button of this Autolab instrument, and then switch on the Nova software. And by this, through this software, there is a protocol. You can set the procedures. So we have already a pre-procedure where we can analyze the cyclic voltammetry. The program looks like this, and or we can have response. We have already, and also we have done the impedance EIS response program. It looks like this. So we have for you already done some pre-results where we can look through the results of this pattern chip, how it's look like. Here is a like 10 micrometer pattern chip, and its EIS response look like for any particular electrode. It's look like this, and it's the Nyquist plot. It's merely not the standard Nyquist plot we use in electrical engineering. It's the modified one. We call it Cole plot. It plots the impedance change of the certain system according to the variance of the real part of the impedance and the imaginary part of the system. Here is automatically the circuit generated. It shows this R resistance is 500 ohms, another R is 500 ohms, and the capacitance is 1 microfarad. So by this we can generate some virtual circuit elements for this chip. So friends, this was a very short introduction of our research on nanocrystalline biosensing. Me and Jonas tried to put together things. Hope you guys have liked it.